Hello and welcome back. In this video we'll start section 2.1. And just as a refresher, we'll do this probably at the beginning of every lecture from now on. Let's remind ourselves of our trig functions. So if we pick a point xy in our plane and we look at the angle between the positive x-axis over here and the line made from the origin to that point, we have this angle which I'll just call theta, and we have the length of the line from the origin up to this point xy, which we call r, and our trig functions. So sine of theta is going to be y divided by r. Y is whatever this number is, positive, negative, whatever it is, divided by r. R is the length, so it's always positive. Cosine of theta, which is going to be x over r, tangent of theta, which is going to be y over x. Cosecant, secant, and cotangent are easy to remember as long as you match them up right, because they're just reciprocals. Cosecant is going to be r divided by y, secant is r divided by x, and cotangent is x divided by y. So we've seen this, and this is going to be really useful. It's really important to remember those, maybe even memorize them. However, when we are just dealing with acute angles, so again, acute angles are going to be angles that are between 90 degrees and 0 degrees. So any angle that's going to be inside of this first quadrant, we can draw a little triangle to sort of help us here. So if I just draw a line straight down, this line is going to make a right angle with the x-axis, and this right angled triangle gives us a little will give us a little bit more information. So for this right triangle here, x is going to be the distance is going to be the length of the side, and y is going to be the height of this side. So again, if we're up here in this first quadrant, we're to the right, so x is positive. We're up, so y is positive. So these guys are lengths, so this makes sense. The length of this side is going to be x, the length of this side is going to be y, the length of the hypotenuse is going to be r. And what we'll notice is that x is the side adjacent to theta. Adjacent meaning sort of connected to, and y is going to be the side opposite. So it's not touching this angle at all, this angle theta. And what we can then write are the following. So sine, which we would normally write as y divided by r, we can kind of think as y as the opposite side to this. So we can think of this as the side opposite to our angle divided by the r, which is going to be the length of the hypotenuse. Cosine, which is going to be x divided by r, so this is the adjacent side, divided by the hypotenuse. And then furthermore, the tangent is going to be y divided by x, and y is going to be the opposite side, divided by the adjacent side. And one thing that I really want to stress is that we're looking at a triangle here. And what can the angles inside of a triangle be? Well, we know that we're looking at a right triangle, so this is going to be 90. The other two angles would have, the three angles inside have to add up to 180. So both of the other angles have to add up to 90. So only acute angles can be in here. This angle and this angle would have to be less than 90 in order for this to be a valid triangle. So when you want to use this is only for, if I could spell, only for acute angles. So if you have non-acute angle, there are extra steps that you'd have to use for this. But for acute angles, this is fairly nice, and we can remember this using SOHCAHTOA. This is maybe something that you've heard before. If we break it down into three things, we have SO, CA, and TOA. SO would be, if I can highlight this in red, sine is opposite over hypotenuse. CA, cosine, is adjacent over hypotenuse. And TOA, tangent, is opposite over adjacent. So this is just a very nice acronym. I'm sure you may have heard this before, at least in some context. If not, it's very handy. It's a nice phrase, SOHCAHTOA, and we can use this to find the sine, cosine, and tangent of angles that are acute by looking at triangles. So let's do an example here. We have, in this drawing here, I have a right triangle, and what I've done is I've labeled the corners A, B, and C. And what is quite often done in trigonometry and just geometry in general is we'll use capital letters for the corners, for these angles, essentially, and then the side opposite that. So C, the side opposite of C, I've labeled little c. The side opposite A is little a, and the side opposite of B is little b. And so A here would correspond to this angle, and B corresponds to this angle down here. So we're told that B, this length is 2. We're told that C, this length is 3. And I know that from the square corner here, this is going to be a right angle. So I know that this is 90 degrees. So the question is, what else can we learn about this? Well, A here, if we know two sides of a right triangle, we can figure out A. So again, the sides of a right angle triangle should satisfy the two sides next to the right angle are going to be A squared plus B squared, and that should add up to be C squared. So I know, for instance, that A squared is going to be, A squared plus 2 squared is equal to 3 squared. Well, 3 squared is 9, 2 squared is 4, so A squared is going to be 5 after I subtract the 4 from the 9. So A is the square root of 5. So let's label these. So instead of A, I'm going to write the square root of 5 here. Instead of C, I was told that C is 3. And instead of B, I know that this is going to be 2. So let's try to figure out sine, cosine, and tangent. And I'm going to use the acronym here, SOHCAHTOA. So sine is going to be opposite over hypotenuse. So the side opposite of A is going to be the square root of 5 over the hypotenuse, which is 3. The cosine of A is going to be, this is CA, so CAH is going to be the adjacent side divided by the hypotenuse. And TOA is going to be opposite over adjacent. So the square root of 5 divided by 2. SOHCAHTOA. And just for completeness, I want to look at the sine, cosine, and tangent of B over here. So for this angle, the opposite, SOHCAHTOA, so sine is opposite over hypotenuse. The side opposite of B is 2, but the hypotenuse is still 3. The hypotenuse will never change. It's only, are we talking about the side opposite or the side adjacent to the angle? That's what's going to change. Cosine, adjacent over hypotenuse. So the side adjacent to B is the square root of 5, and the hypotenuse is 3. And then tangent is going to be opposite over adjacent. And with this textbook, they want us to rationalize fractions. So we don't want this square root of 5 on the bottom. So I'll multiply by the square root of 5 divided by the square root of 5 to cancel out. And what we're left with is 2 root 5 over 5. And this is how we use SOHCAHTOA. It's fairly straightforward. And this does illustrate one other thing. I want to point out that the sine of A up here and the cosine of B are the same. And this is not a coincidence. Likewise, the cosine of A and the sine of B are also the same. Again, this is not a coincidence. If we think about the sine of A is going to be the opposite side for A divided by the hypotenuse. For B, the cosine of B is going to be the side adjacent to B divided by the hypotenuse. The side opposite of A is adjacent to B, and for B, the side opposite of B is the side that's adjacent to A. So adjacent and opposite will switch when we go from one corner, from one angle to the other, which means that the sine and cosine are going to flip. The sine and cosine are almost exactly the same, except one uses the opposite and one uses the adjacent. These are called cofunctions. So when we look at sine and cosine, for instance, you'll notice that it's sine and cosine. It's secant and cosecant, tangent and cotangent. And all of these arise essentially from looking at these triangles and noticing that the opposites and adjacents will switch if we go from one angle to the other angle. So what's special about A and B? Well, the three angles in a triangle have to add up to 180, so we can write that down. A plus B plus C has to be equal to 180. But we know what C is. C is a 90-degree angle. So if I subtract 90 from both sides, I get A plus B is 90. So more so than anything else, A and B are complementary. If I can fit that in. And what I'm going to point out is that this is going to be easy to remember because we've got CO again, in the same way that we have CO, CO, and CO. Okay, so the cofunction identities are listed here. Sine and cosines are equal for complementary angles. So if you take an angle, theta, and you find its complementary angle, if you plug one into sine and the other into cosine, they're equal to one another. Likewise, we don't have to do sine first and cosine second. If you find an angle and you plug it into cosine, and you find its complementary angle and plug it into sine, they're equal. Likewise, for secant and cosecant, and tangent and cotangent. The co here doesn't officially stand for complement, but it's nice and convenient that they both begin with CO. Cosine, cosecant, and cotangent. They all play very nicely with complementary angles. So let's just do a couple of examples. So let's say that I have sine of a 30-degree angle. If I wanted to use my cofunction identities, sine and cosine are going to be equal. And what I need is the complementary angle to 30 degrees. So what I'll do is I'll take 90 degrees minus 30 degrees, and I'll get the cosine of a 60-degree angle. 60 and 30 are complementary, so sine of 30 and cosine of 60 are equal. We can do the same thing with cosecant. Cosecant and secant will be equal when we plug in complementary angles. So 90 minus 11 is going to be 89. So when we plug in complementary angles, we get the same thing. And I'll continue to look at this in the next video.